Good morning. Good morning. I think we can start. My name is Mark Brierley, and I'm talking about the Warm War. This title came from something I read. I think it was a book by Kohei Saito. If you know Kohei Saito. In the book it said that since after the end of the Cold War, there have been more carbon emissions than until the end of the Cold War, the whole of human history. And this is in my lifetime. I think this is in your lifetime. And this seemed very interesting why this has happened. So I have I'm going to start with two things. First of all, I have a few questions I want you to think about. I'm going to speak in English. Hope that's okay. I'll try to speak in easy English. And here are some questions. First is, how's the weather? The second one is, how is the climate? The next question is, what is climate? And the next question, why isn't the Earth frozen? And the next question, is it getting warmer? Some of these. And if we want to use the air conditioner, we can use the air conditioner. Good, nice timing. Okay, thank you. Wonderful, good. So yes, well, hopefully we will know more by the end of today. But we're going to start with let's start with a kind of, when we're saying it's getting hotter, or if we're asking, is it getting hotter? A very basic question is, what is hot? What does hot actually mean? And we've talked, as Seiichi will remember, I think from, we've talked about this before. And we need to talk about thermodynamics. Maybe some of you know thermodynamics. Maybe you know the second law of thermodynamics. Do you know the second law of thermodynamics? Yes? No? No? Do you know the first law of thermodynamics? Yes. You don't even know the first law. So we're going to look at the. You may know these, but you may not know that you know them. And the topics I'm going to try and think about first are about energy, and about power, and about the units, how we measure, and how we consider energy. And also another very important question for the whole of this topic, accuracy and precision are very important. How do we know, how sure are we about what we know? If someone says this is 5%, how do they know, is it exactly 5%, or is it maybe it's 10%? So that's a very important issue in this topic. Energy is important to understand. If we want to understand what is happening, why do we have storms in Spain? Why is it hotter than? I moved to Matsumoto. The first time I came to Matsumoto was in the 1980s, in the end of the 1980s, and it's a lot hotter now than it was before. Why are we getting more flooded weather? Why is the severe winters maybe not so severe? So this is all connected to energy. And if to understand what's happening, we need to understand first of all what are the basics. What's the very basic physics behind this? So the energy problem. We often hear about the energy problem in the news. I don't know if you drive. If you drive a car, you may have noticed the price of your gasoline has gone up. That's one energy problem. The other energy problem is a more basic scientific question. What is energy? How do we? So let's just start thinking. How do we? If you want to measure length, then we measure length in meters. If you want to measure mass, how heavy something is, we use kilograms. How about energy? How do we measure? I'd like you to talk to each other. There may be more than one answer. Yeah, no, calories. Yes, calorie is good. Yeah. Calorie is that's not my next one. Calories is the third one in my list. Actually, the second one is not watts, but actually kilowatt hours. If you buy electricity, probably you do buy electricity. If you look at your electricity bill, it's measured the amount of energy. You're buying energy. When you buy electricity, you're buying energy. And kilowatt hours is the measure that they use when you buy electricity. If you go to the supermarket, when I go to the supermarket, I'm quite thin, so I want energy. So usually I look, and on food it says calories, and usually I look for something what's got the most calories. I don't try to get the least. Some people try to get the least calories, but if I'm buying something from the supermarket, I want to buy calories because that's the energy. And food is not just energy, but food for energy is measured in calories. If you're buying oil, if you're buying oil for your heater, maybe toilet heater, or if you're buying gas for your car, as energy, the litres of oil is also a measure of how much energy. If you're buying gas, usually we think about how many cubic meters of gas, and each cubic meter of gas contains a certain amount of energy. If your phone has a battery, the battery in your phone stores energy, and that will be measured in amp hours. So if you're getting a new battery, you can see how much does the battery hold, will be measured in amp hours or milliamp hours. BTU, British Thermal Units, are used in America. This is an old English measurement system for measuring energy. Electron volts, if you're looking at energy at small scales at the atomic level, we measure electron volts. As you may remember, as Einstein said, E equals mc squared. And Newton meters, also energy. If you have an object, if you lift it, the force over distance is energy. So energy is quite it's quite complicated. It's not a simple thing like length or like weight. Energy is a bit more complicated, and we measure it in different ways depending on how we're using it. Do you have a question? No. I'm just going to talk about. Let's talk about Joule. This is James Joule, who was actually his main job was making beer. He had a brewery in Manchester, and at the time, the brewery maybe looks something like this. So when you're making beer, I don't know. Have you ever made beer? No. If you make beer, two things are very important with beer. The temperature is very important because beer uses yeast is turning sugars into alcohol. So the temperature is very important for making good beer. If it's too cold, the yeast will not work. If it's too hot, then you can get other bacteria. So temperature is very, very important. At the time he was making beer, a couple of things were happening, and this is the ingredients, not of beer, but the ingredients of science, which are, he wanted constant temperature beer, and he had, at the time they had very accurate thermometers, so they could measure the temperature of the beer very accurately. And at the time also there was a great interest in science around this time in England in the 1800s, and what this led to was he discovered what was later called the first law of thermodynamics, and he found out that if he stirred the beer, it made the temperature go up. So he worked out that putting this kind of energy into the beer resulted in a higher temperature. So what's happening in that case is that energy is turning into heat, and the energy is work, and so work can be energy, and heat can be energy, and what's moving is what's changing is the energy is changing. So the energy is changing form, but he also realized that you can't make energy, and you cannot destroy energy. The energy just goes from one form to the other. So the energy is going from work. By stirring, the temperature goes up, so it's going into heat inside the beer. So this is the first law of thermodynamics. Very basic law. Energy cannot disappear, and energy cannot be created. It can just move from one place to another, or from one form to another. This is 1 joule. 1 joule is the energy needed to move 1 Newton 1 meter. So before Joule made this discovery, and before he made this discovery, people had many different ideas about energy, about what energy was, and one of them is caloric. And some people thought that energy was like a substance. There was an idea of phlogiston. People found that if they people have always, this is something we'll come back to later, people always they look at the world and think, why is this happening? And they think, oh, I have an idea. It's happening because this. And often these ideas are wrong. So often the way that our explanation for why things are happening are wrong. And we'll talk more about science. Science is how we find out what is true and what is happening. So the earliest scientific ideas for energy were caloric and phlogiston. The idea of phlogiston is that heat is a substance. The idea of caloric is where we get the word calorie, which we still use. So we still use the word calorie, which is based on science that is wrong. Phlogiston, this is an idea from 1690s, and the idea was that wood contained this substance called phlogiston. So when you burn it, the phlogiston is released, and it leaves you with ash. So the idea was that wood was made up of ash plus phlogiston, and if you burn wood, the phlogiston is released, and you're left with the ash. So they thought this is a good theory. This makes sense. It explains why something is happening, but it's not actually correct. A later idea, I think, was the idea of caloric, and this was that there's some igneous fluid. So there's some like a liquid, and this liquid becomes heat. So again, this explains. So when you heat things up, they expand. So this is the idea that heat is a substance, and again, this is wrong. Heat is not stuff. Here's a question for you. So here's a question: which is hotter, 1 litre of hot air, or 1 litre of hot water? Please discuss. What do you think? Which one is hotter? Okay, and sorry to this is a trick question because they're both hot means what temperature, and they're both the same temperature. But the question that you're thinking about is which one has. Yeah, so when we say hotter, it means higher temperature. But that does not exactly mean that. Usually, if something has more heat, the temperature is higher. But heat is not temperature. And if you think of if you think of which of these has more heat, 1 litre of hot air, the question that you're thinking about, and just to imagine if it's cold and you want to make your bed warm, will you put in a hot water bottle or a hot air bottle? Which do you think? And yeah, you'll use a U-tampo. Yeah, not a There is no air sample. Yeah. So we know that a liter of, so this is energy. A liter of hot air has less energy. A liter of hot water has more energy. How many times more? Would you have a guess? How many times? So if you wanted to use hot air bottles to make your bed warm, how many would you need? Instead of, what do you think? Have a guess. Have a guess.
10,000 times.
Well, 10,000 times. Okay. Yeah, we can. I don't think this is not a maths lesson, but we can calculate this. There is a function. There's a value called heat capacity, and the heat capacity is how much energy is released if you change the temperature by 1 degree of 1 unit. So, for example, this is the specific heat capacity times the mass. So how heavy? So for the hot water bottle, we've got 1 kilogram of water. 1 liter is 1 kilogram. And if we know the heat capacity of water, we know how much energy is in 1 degree change of hot water. And there's also a volume. So with the gas, it's more volume, maybe, than the mass. So we can work this out. We know the unit for air. Water is about 4.2 kilojoules per kilogram Kelvin. And actually, there is an important bit of science here when we're writing about units, and units do become very important because when we're trying to measure things, we need to know what we are measuring. The little k is kilo. Kilo means 1,000, so a kilojoule is 1,000 joules. A kilogram, again, small k, is 1,000 grams. And this big K is Kelvin. Kelvin is a measure of temperature. Kelvin is the same as centigrade, but it starts 273 degrees lower. So centigrade 0 is when water is frozen. Kelvin 0 is when the universe stops. So absolute 0 is the 0 for Kelvin, which is much colder than freezing. So the K, if it's a person's name, and J is Joule. Joule is named after a person, so we use a capital letter for Joule. Kelvin is named after a person. We use a capital letter for Kelvin. Kilo and gram are not named after people, so they're small k's. So we sometimes get confused between a big K and a small k, and this is an important difference. So we know that this is 4.2 kilojoules per kilogram Kelvin, and air is 1.2 kilojoules per cubic meter Kelvin. Now a cubic meter is many liters. 1,000 liters? 1,000 liters? One cubic meter. I think 1 cubic meter is 1,000 meters. So we can see very quickly, because we're talking about kilograms here and cubic meters here, we can see that this is at least 1,000 times more. Because a cubic meter of air, we're not comparing kilograms and kilograms. And also we can see that 4.2 is bigger than 1.2. So it's more than 20. It's less than 10,000. That's a good guess. It's more like, just here's a picture of Lord Kelvin, who was I think Kelvin was maybe Irish. Maybe he's from Ireland. Joule was from Manchester. Joule was English. I think Kelvin was maybe Irish, maybe Scottish. So how many times more heat? We can work it out. We can work out if we say the temperature difference is 80 degrees, we're going from 20. The hot water was 80 degrees. If it cools down, it's going to be 20. So how much temperature will it release? and let's say 60 Kelvin. So we can work out all these. We can work this out. We know the density of water, 1 kilogram per liter. We know this formula for how much energy is specific heat capacity times mass times temperature difference. So it's 4.2 times 1 times 60. So this is how much energy is in the 1 litre of water. Okay, so we can compare this, we can do a similar calculation for air. We have to remember that 1 litre is 0.001 cubic meters. And the energy is something like this. So this is 72 joules. So we're comparing 72 joules with 270,000. So the answer is the water has over 3,000 times more heat. So if you want to use a hot air bottle instead of a hot water bottle, you need 3,000. Now, let's just talk a little bit about accuracy and precision here. So this is an example of accuracy or precision. This is very high precision. We've got hours, minutes, and seconds. But this may be more accurate. It's not both. Neither of them are accurate. It's 10:45. Both of these are wrong. But that one has more precision. And it's just to show you on a target board. This is high precision and high accuracy. This is high precision. Everything is very close together, but it's not accurate. This one is quite high accuracy. They're all quite near the target, but not actually on the target. And this one is low accuracy and low precision. So precision and accuracy are two different measurements. And just to give you another example of this, which of these? One of these is more accurate. One of these is more precise. This is a pi. Any idea?
What was the question?
Which of these numbers? Pi is 3.14. Pi is a bit over 3. One of these is more accurate. One of these is more precise. Which one is precise? Which one is accurate?
Maybe upper number is accurate and below is precisely precise.
I think it's the other way around. I think this is more. This number, I made this number up. Okay. This is not pi. The beginning. This is pi is 3.14. It's not 2. This is all made up. Very precise. Very, very precise. It's exact, but it's not correct. Whereas pi is a bit over 3. This is completely accurate. Pi is a bit over 3. It's not under 3. It's not over 4. So this is accuracy, and this is precision. And often these are confused. And often when we see precision, we think this must be accurate. Oh wow, there are lots of numbers. They must be true. But beware. Just having lots of numbers does not make something true. It doesn't make it more accurate. And often you don't need. So, for example, in the case of that's what pi actually is. Often pi is a bit. Often, if you're doing a calculation, if you're trying to buy some rope, and you want pi is a bit over 3, is often enough to get a good calculation. And in this case as well, the water has over 3,000 times more heat. If you're trying to make your bed warm and trying to decide should I use hot water, then you don't need to know whether it's 3,000 or 2,000 or even 100. You just need to. It doesn't matter how whether it's 3,000. You don't need that much precision. And in fact, when we did the calculation, we were taking quite precise numbers and believing them. However, this is the specific heat capacity of water, and it changes with temperature. So it's around 4.2, and at this temperature, at 7 degrees, the amount of heat that water can hold is 4.2 joules per kilogram. But as it gets hotter, it can hold a little bit less heat, and then when it gets hotter again, it can hold a little bit more heat. So this number, this 4.2 number that we used, it's not exactly 4.2. It's around 4.2, but there's an error. There's a range. And similarly, water. We know that 1 litre of water weighs 1 kilogram, but again, that changes with temperature. So it's not exactly 1 kilogram. If the water is at 80 degrees, it's a little bit less than 1 kilogram. So all of the numbers that we put into our calculation, they have a range. It's not precisely this number. And similarly, the density of air changes quite a lot as the temperature changes. The water density is somewhere between that. The water heat capacity is between these numbers. The air density, there's quite a big range of air density. The air heat capacity also changes quite a bit in this temperature range. And another, to get more complicated, is the air staying at constant volume or is it staying at constant pressure? So whether the bottles are plastic bottles that will expand, or if we have solid bottles, that will make a difference to this what's happening. So the question is, it's a very simple question, and we know the answer. But if we want to find if we want to calculate the answer, then when we get to precision. But as I said, we don't need to know this. In this case, this is all we need to know. And in many cases, that is all we need to know. But it's important to know what we don't know. And if we're using a number, are we saying? Because if we say so no, you need to know how accurate are the numbers going in. If we say 4, what 4 actually means is somewhere between 3.5 and 4.5. So we're saying there's an error. There's like a 10% error or 10% range of answers. If we say something is 4.2, what we're saying is it's between 4.15 and 4.25. So this is like a 1% error. And if we're saying it's 4.18, then that's a 0.1% error. So the numbers that we use, there's also an error. There's a range of the number. And this is important to understand science, and lots of we'll talk more about that later. But we need so energy change. So energy is, we cannot create energy, we cannot make energy, but it can change from one form to another. For example, there's mechanical energy. So if something is moving, it has energy. There's also potential energy. So if I lift something up here, this has some energy. If I let go, it's going to fall to the ground. There is also thermal energy, so heat. There's chemical energy. So within atoms, between atoms joining together, they have energy when two atoms join together, when they release. This is what happens when we burn something. The atoms are joining or separating or joining. There's nuclear energy. So within the atoms there is energy. There's electrical energy, electromagnetic energy, magnetic energy, and here are some. Oh, here you go. So here's a question for you. So energy. So how much? This is another question to think about energy around us. How much energy is in 1 litre of paraffin? 1 litre of toyu. How much energy is in 1 smartphone battery? How much energy is in 1 onigiri? How much is in 1 litre of hot water? And how much is in 1 gram of uranium? Could you try and put these in order? Which of these has the most energy? Which of these has the least energy? And try and get them in order from most energy to least energy. Please, sir. Okay, I'll come to the answers later. I'm just going to introduce another person. We've seen his name, and you've heard his name before. This is Watt. James Watt, I think, was Scottish, and his name is used for power. And he was an inventor and a businessman, and he was good at inventing and was good at business. His invention, he made a steam engine. He didn't make the first steam engine, but I think he made a very important improvement to the steam engine. The way that steam engines work is it heats up water. The water turns to steam. The steam expands. The steam pushes this, and then the steam condenses and contracts. And I think the early steam engines, the steam would do the work and then would be lost into the atmosphere. So the steam engines worked, but then you ran out of water. And I think Watt's development was he made a cycle so the steam is kept within the system. And this means that you don't lose the water and that the steam engine will keep working. And at first, the steam engine was used in Scotland. They were mining for coal, so they were digging underground for coal. And same problem with the city, flooding. If you dig a hole in the ground, it will fill up with water. So they used a pump. They need a pump to remove the water from the mine. And if you remove the water from the mine, you can dig more coal. So they were using this steam engine for pumping water out of the coal mine so they can dig more coal. So more coal goes into the steam engine, more water taken out, dig more coal. And then they started using this same steam engine for moving coal. And then more people can burn the coal. And then other places can use the steam engine. So this spread. And this is I think this is the beginning of our problems with climate and with carbon dioxide in the atmosphere. And I think this is kind of still going on. And what happens is the more this works, the more coal you can produce. And the more coal you produce, the more you can burn, and the more engines you can make. And it's a cycle that gets bigger and bigger and worse and worse. So or more. So that's Watt's invention. As far as science is concerned, Watt also comes with the unit of the watt is power, and power is the rate at which energy is changing. So as we saw before, we have energy. We can buy electricity. We can buy a rice ball. We can get a bottle of hot water. That's all energy. and energy changes from one form to another, and the speed it's changing at is power. Power has many meanings. This is meaning 6C, but this is the scientific meaning for power. And also energy and power, again, these are often confused as to what is energy and what is power. Before we also confused with heat and temperature. And when we're talking, our language does not do a good job of a scientific job of deciding which is which. So power is basically movement or change of energy. And 1 watt is 1 joule per second. So if you're changing energy or moving energy, 1 joule per second, that's 1 watt. That's some notes. So let's just think about a few things. So shower. Is that power or is that energy? A car. Power, energy. An oil tanker. An oil tanker is a large ship now stuck in Hormuz somewhere that's full of oil. Is that energy or power? A piece of wood, energy or power? A battery, energy or power? A solar panel, an air conditioner, fat, muscle, sunshine, a reservoir. So, please talk to each other. What do you think? Which do you think mostly are these energy or are these power? So, what do you think? Shower is energy, power, energy, power, power. Yeah, I think shower is power. A car is energy, power, power. Good. Yeah. Oil tanker is energy. Energy. Yeah, it's full of oil. The oil is energy. A piece of wood, energy, power, energy. I think a piece of wood is energy. If you burn it, it will turn into heat. A battery, energy. Yep, good. A solar panel, energy, power. I think a solar panel is power. It doesn't keep energy. It changes the sunlight into electricity. Air conditioner, energy, power. Good, yeah. Fat, energy. Good, yeah. Fat is energy. Muscle, energy, power. So muscle is power. Muscle is turning energy into work. Sunshine, energy, power. I think sunshine is power. So the sun is there's a nuclear reaction. Sun is changing hydrogen into helium. I think hydrogen atoms into helium, and then the sunshine is changing. The power is being sent up. A reservoir, energy, power. Yeah, I think a reservoir is a store of water up in the mountains. It's energy, so we can use that energy. And wind is energy, power. Power. Wind is power. Okay. So we can see. You have a question?
I just don't know the meaning of
Reservoir. Reservoir is a dam. Dam.
Oh, dam. Okay.
I should say dam. Sorry, dam is an easy word. Reservoir. Yeah. Right. Yeah. Dam. Actually, a dam is the wall, and the reservoir is the water. So in fact, it's not the same as a dam. The dam is just the dam is this bit. The reservoir is the water, store of water. It's called a reservoir. So great. So sorry, there's an oil tanker. Here's a power question. Which do you think uses the most power? A computer, an air conditioner, a shower, a kettle, or you climbing the stairs? Yes. So this is homework. This is your homework. Power. So power is the unit of power is watt. So 1 watt is one. And just to be this is a bit confusing. A kilowatt hour is if you have 1 kilowatt running for 1 hour, that's 1 kilowatt hour. So a kilowatt hour is a measurement of energy. Watts of power, kilowatt hours are energy. So one kilowatt hour is 3,600,000 joules, or 860 kilocalories. Joules are very. I have a lot of trouble understanding joules. A kilowatt hour is quite a tangible unit. It's quite easy to understand and visualize what a kilowatt hour is. Electron volts also difficult to think about. So 1 kilowatt hour is if you have a 100 watt light bulb and you run that for 10 hours, that's 1 kilowatt hour. If you have 0.04 milligrams of uranium, a very, very small amount of uranium is 1 kilowatt hour. If you have a litre of paraffin has about 10 kilowatt hours, which is quite energy dense. It's quite not as much as uranium. Uranium has a lot more energy than paraffin. And similarly, 1.1 cubic metre of gas is also about 1 kilowatt hour. 5 rice balls is 1 kilowatt hour. We want to convert into the rice ball as the unit of energy. So 5 rice balls is about, so a litre of paraffin is about 50 rice balls. If you want to think about how much energy, how you're comparing the energy. And about 20 litres of hot water. If you want to boil 20 kettles, that's 1 kilowatt hour. And 100 smartphone batteries. A smartphone battery, about 100 batteries is 1 kilowatt hour. So smartphone batteries are getting better all the time, steadily. And 500 stories. So you can climb 500. That's like Tokyo Tower, maybe. You can climb to the top of Tokyo Tower. So what for me is very interesting. If you're worried about losing weight, then eat less rice balls, because 5 rice balls is 500 stories of carbs. So exercise is important. Exercise is a good idea, but the amounts of energy that you're taking in, there's a yes. Anyway, so heat moves. So if we're talking about heat moving. Heat can move by conduction, convection, or radiation, conduction is moving through a substance, convection is a fluid moving, and radiation is electromagnetic waves, or in Japanese these are Dendo, Tairyu, and Horsha. So this is the way that heat is moving. When energy is moving as heat, and I think these all affect the weather and the climate. So these all affect our story. So which kind of heat transfer do you think is happening across a room, through a wall, inside a kettle, in your clothes, from a fire, or from a flat roof on a cloudless night? Of the 3, conduction, convection, radiation, which one? Please discuss. Please. Okay, so I think conduction, convection. I think heat moving across a room is convection. I think the heat is moving, the air is getting hotter, and the air is carrying the heat across the room. Through a wall is conduction. From a spaceship is radiation. Inside a kettle is convection, so the water is getting hotter and moving. In your clothes is mostly conduction. Mostly, I think. There's some convection, some radiation. From a fire is radiation, and also from a flat roof on a cloudless night, your roof is radiating into space. So which way does heat move? Heat moves from hot to cold. This is basically the second law. It's very simple. The second law of thermodynamics. The first law of thermodynamics tells us that heat and work are related, and they are energy, and that energy is conserved. And the second law basically tells us that heat goes from hot to cold. This was two scientists, French and German, I think, who discovered this in the 1800s. And the second law of thermodynamics basically says that heat goes from hot to cold. So if you have tea, if you don't drink your tea, nuruku naru is a very useful Japanese, very good use of Japanese, because if it's hot tea, it will become nuri, and if it's cold tea, it will also become nuri. So it's kind of going towards room temperature, and entropy increases. So if you can't make a smoothie into a banana. You can turn a banana into a smoothie. Your room will get messy. It will not get tidy naturally. Things tend to become more chaotic and more messy, and we need to work to keep things tidy. So Earth. Let's just think very simply what we've talked about in terms of energy. If we think of Earth as a system, think of our planet as one system, then what's happening is the sun, radiation is coming into the sun, radiation is coming from the sun and making it hotter, and then the Earth is emitting radiation. We're not conducting into space. There's no convection into space. So the system heat is coming in, energy is coming in by radiation from the sun, and then we're radiating out. So it's something like this. In the daytime, or in one side of the Earth, the sun is heating up, and then the Earth is sending out the heat by radiation. Now, if we remember the balance, if the amount of energy coming in is the same as the energy going out, then we have a constant average temperature. Okay? And if not, for example, if more energy comes in and less energy goes out, then the temperature goes up. Okay? So the same as, so we know this. So and we can see, if we look at these are the other planets in the solar system. This is Mercury, there's Mars, Jupiter, Saturn, Uranus, Neptune. Even Pluto is on the list. I'll talk about Pluto later. And you can see this is how far they are from the sun. So you can see, as you can imagine, if it's far from the sun, it gets less heat from the sun. So that the planets are cooler far away from the sun. Yeah. So this makes sense. This follows the sun's. One planet is missing. Which planet is missing? The Earth is here. I got it. I thought Earth there. One planet is missing. Which planet is missing? Cece. Venus is missing, yeah. So Venus, let me just put Venus in. Venus is here. Venus is much, much hotter than it should be, although much, much hotter than the trend based on just a lump of rock or lump of gas. Why why is Venus so much hotter? Why is Venus so much hotter? CO2, yeah, Venus has an atmosphere. So it's got like it's kind of like a down jacket. It's like it's wearing this very high quality down jacket, which keeps it very warm. So so the question, why isn't Earth? This question, scientists have been thinking about this for a while. In the 1820s, Joseph Fourier, French scientist, wondered why he looked at the Earth and where the sun is, and thought that the Earth should be much colder. And later. So as far as Earth also has an atmosphere. It's not as thick as the atmosphere on Venus. Venus has a very thick, very heavy atmosphere. The Earth's atmosphere, what do you know about the atmosphere? What is in our atmosphere? How thick is the Earth's atmosphere? If our atmosphere was liquid, the atmosphere is gas. If it was liquid, how thick do you think it would be? Yes. So yeah, the atmosphere is nitrogen. I'll talk about. I think it's about 100 kilometers thick. I think the atmosphere is very thin for the size. I think if it was liquid, it would only be about 10 meters. So if the atmosphere was liquid, we would be able to. If we went, it would be about this. This would be space. About 10 meters above the ground. So it is very thin. We have a very thin atmosphere, but it is also. It's not just thin. It is very important because we need to breathe. We like oxygen. Also it's stopped, so some of the radiation is stopped by the atmosphere. And different frequencies, so radiation has different frequencies, and different frequencies are stopped different amounts. It's like a filter that will stop some frequencies more and some frequencies other. Before we talked about radiation from the sun, the radiation coming into the Earth and the radiation leaving the Earth is affected differently by the atmosphere. The radiation, this is the wavelength. So the sun is very short wavelength, very high frequency, high energy. It's kind of like bullets being shot through. And the Earth, the radiation from the Earth is lower energy, so it's longer wavelength, and it's longer wavelength and lower so it's kind of like balloons. So the radiation from the Earth is kind of like balloons, and between them there's a filter. The atmosphere is a filter, and it will stop the balloons better than it will stop the bullets. So this is the wavelength. This is the sun. The spectrum is what we can see. So we can see the sun's, most of the high energy radiation from the sun is what we can see, because that's useful for us. The radiation, this is infrared radiation. This is lower energy radiation, which we can't see, but we can feel as temperature. So the Earth is radiating. The Earth is radiating back down in this range, and you can see some troughs in here. Now the Earth the Earth loses energy by radiation, and the balance is important. So the energy is coming from the sun to the Earth and then radiating out again to space. And if this balance changes, then the temperature will go up. And it's the energy. It's energy. How much energy is in the system? And that energy becomes storms in Spain. And that energy becomes more rain in Suez. So the energy directly affects the climate. And what's happening, and also this is happening over time. So over time, things accumulate. These are some of the important. Most of the atmosphere is nitrogen. Nitrogen is 2 nitrogen atoms. Oxygen is the second most, maybe the most important for us, the second biggest. There's also a lot of humidity, a lot of water in the atmosphere. There's carbon dioxide, ozone, methane. And these gases, some of these are what are called greenhouse gases. And as you can see, with most of these have like 3, where there are 3 atoms, what happens within the atom is that it's like a guitar string. If you hit a guitar string, you get a nice ringing sound. And some of these atoms act a bit like guitar strings, that they will take energy. And like a guitar string, they have a frequency. So these atoms have frequencies, and if they get radiation at the right frequency, they will take energy. They'll get excited, and they will take energy from the radiation. So these frequencies, we can see these frequencies. These are the frequencies for methane. Methane is in natural gas. A lot of the, maybe not a lot, some of the natural gas, when we buy gas, they lose some on the way getting to our house. And some of that gas goes into the atmosphere. And at these frequencies, methane absorbs lots of energy. Nitrogen oxide has different frequencies. It's a different size. Like a guitar, if you have a thicker string or a longer string or shorter string, it changes the frequency. So these atoms, carbon dioxide, these frequencies are where carbon dioxide is activated. So that when we put all these together into the atmosphere, there are some frequencies where the atmosphere absorbs energy. And most of these frequencies are the energy that's coming from the Earth to the sun. So it is not affecting the balance equally. It's stopping heat from leaving the system. And as we saw before, if we have more energy coming in and less energy getting out, it'll get hotter. So this is basically what's happening with global warming. This is not new. This is not a new idea. As I said, Fourier noticed that the temperature, that the Earth was hotter than it should be in 200 years ago. This is John Tyndall, who measured gases in a laboratory and found that carbon dioxide and water were absorbing infrared radiation. So he worked out the mechanism in the 1850s, 1860s. He worked out the mechanism for global warming, for how the planet absorbs heat. Svante Arrhenius, who I think it was Swedish, 1896, he worked out that more carbon dioxide was going to lead to a warmer Earth. So none of this is really new. And by the way, I think his maybe granddaughter is Greta Thunberg. I think. Not sure, but I think there's a family connection. But the science is not. The science is old. The science is well established, and also I think the science is quite easy. I think the science is quite easy to understand. I think that's all we have time for today. That's all we have time for today. We've covered. This is the easy part. The easy part is the science. From next week, we're going to talk about the more difficult parts, which are politics and economics, and politics and economics.